Hello and welcome to section 3.2 Rolle's Theorem and Mean Value Theorem. Remember, if you have any questions on these examples, please come to class prepared to ask them. So we're going to talk about finding the x-intercepts, and we're going to show that there's an f prime of 0 at some point between the x-intercepts. This is Rolle's theorem, and in Rolle's theorem basically we're asked to find, it's an existence theorem, and the existence theorem proves that there is a horizontal tangent somewhere in the graph. And so we're going to kind of use that as our guideline. So the first thing I'm going to do is find the x-intercepts. That's what they want me to do. So I'm going to set 0 equals x squared minus 3x plus 2. And if I factor that, you can see that I get x minus 1 and x plus minus 2. And so then if I solve that, that means my x-intercepts are 1 and 2. So that's where the graph is crossing the x-axis. And so if you think about this, as you probably got some kind of parabola that's looking like this, and it's going to come down and cross at 1 and 2. And so you can see that these guys would be my where x is equal to 0. So using Rolle's theorem, we would first go, okay, well, what happens since we have our interval now of 1 to 2? Our interval is from 1 to 2. On a closed interval, we would check and see if what f of 1 equals, and we would check what f of 2 equals, because if they equal the same thing, then we know that somewhere between those, the graph turns back on itself and gives you a horizontal tangent at least once. Well, in this case, I already found these guys because how we did it, we've said they were both equal to 0, so Rolle's theorem is going to work. And how I got these guys were both equal to 0. You could plug them back into the original function, which is what I would normally do. But since I already went through and said the function was equal to 0 and solved them to get those numbers, I already did that work, so I'm not going to bother doing that again. And so now, since that happens, now I can go ahead and find that at some point between these intercepts, we're going to find out that there is going to be a place where the graph turns back on itself. So how I do that is I take the derivative of the function, and we're just going to then look for where does this graph equal 0, because where do we get a horizontal tangent? So I set the derivative equal to 0, and I solve for x. And so I add 3 and divide by 2, so x is 3/2, and that value is somewhere between 1 and 2 on the graph. And so down here somewhere I would have a horizontal tangent on my graph that would be, well, it's supposed to be horizontal, but it would be a horizontal tangent on my graph that would give me, basically we just showed using Rolle's theorem that this worked. So we have an example 2 that deals with Rolle's theorem also. In example 2, we have this function. This time they gave us an interval from -1 to -2 to 2, and we want to find the c values or values where this graph has a horizontal tangent. So again, Rolle's theorem. But if Rolle's theorem is going to work, we're going to have to find out what the what the function's value is at -2 and at +2. So I'm going to go ahead and plug in -2 into the function. And if they come out to be the same, then Rolle's theorem will work for us. And so then it looks like I get 16 minus 8, which gives me a value of 8. And then f of 2, well, plugging it in, will give me, again, 16 minus 8, which means that since these guys are the same, then somewhere in this function the graph is going to cross, somewhere in this interval, the graph is going to have a horizontal tangent. And now if you know anything about this function, it is a W shape, so it's probably going to do something like this. The question is, if this is 8 at -2 and this is 8 at +2, is this the whole thing going on, or is it just going to be like one bump up and stuff like that? So we're going to kind of have to look for that. And so now what we do is we take the derivative of the function. So Rolle's theorem is going to apply, because not only are these guys equal to each other, but this function is a polynomial, which means it's differentiable in that interval. And you always need to kind of check that too, because sometimes the function isn't. Sometimes it's an absolute value or something like that. You just got to be careful. So I'm going to take f prime, and I end up with 4x cubed minus 4x. And so if I do a little factoring, I get something that looks like this. And now I can set it equal to 0, because that's really what I want. And when I set it equal to 0, I can say 4x equals 0, and I can say x minus 1 equals 0. x squared, sorry, those are supposed to be squared when I factored. And so then I can say x squared minus 1 equals 0. So in this case, x is 0, and x is plus or minus 1. And so that means that the horizontal tangent, there's actually 3 of them in this interval because negative 1 fits in the interval, 0 and positive 1. So these are the 3 values where I have horizontal tangents. So then in the next example, we are going to talk about the mean value theorem. And the mean value theorem basically says that if you set the slope of the function equal to the average value, then you can excuse me, then you can find any slope. Where in Rolle's theorem we're only looking for horizontal tangents, in the mean value theorem we're trying to find any slope that will work. So this is the function that we're going to use. This part right here, remember, is average, and it's just the standard slope that we're used to using the secant line, and over here is instantaneous. So basically what we're doing is we're saying in some interval, can we have the same slope, here's our secant line, can we have a derivative slope that is parallel to that? And so we're going to show that we're going to find a slope using average value, and then we're going to set it equal to the derivative, and we'll find that x value where that slope is the same. And that's what mean value theorem is all about. I rewrote the function because when I take the derivative it'll make my life a little bit easier. But first we're going to calculate what the average value is. So I'm going to call it average value, and that's that f of 4 minus f of 1 over 4 minus 1, standard old slope. And plugging in 4 into the function, I end up with 4 minus plugging in 1 into the function, I get 1, and then over 4 minus 1. So hopefully you can see that the slope of this, the average value slope, is 1. And so then if I take the derivative of this function over here, if I take the derivative of f of x, I will then set it equal to the slope that I just found, and then solve. So I'm going to write this as 4 over x squared. And so when I set these guys equal to each other, the mean value theorem says, well, I have a slope of 1 that I'm looking to find in the derivative of the function, or in the original function, where the slopes are the same. So I'm going to cross multiply and get x squared equals 4, and so x will equal plus or minus 2. And if that's the case, if I get plus or minus 2, then that would mean that in the interval, the only one that's going to work is where x is equal to 2. So this is where the value, where we have the same slope in the function. And we have this final example where we have a semi speeding between 2 cop cars. We're going to start out with time 0, and 4 minutes later it's going to pass the other car, and it's going to take 5 miles to get there. So the first thing I'm going to do is say, oh, well, my time is 4 minutes out of 60. And we're trying to prove that the semi had to speed to get from one cop car to the next. And so that's 1/15 of an hour, and which will help us with our miles per hour. And so then what we're going to end up doing is we're going to say, okay, if we have to prove this, we're just going to use our average value. So we're going to say the function in terms of 1/15 minus the function in terms of 0, all divided by 1/15 minus 0. And so then plugging in these values real quick, s of 1/15 was 5 miles, that's how far it traveled, s of 0 is 0, and then we're dividing by 1/15 hours. And so then multiplying this out, we will show that it is 75 miles per hour that the semi had to travel to get between the 2 cop cars using our average value. So this concludes our section 3.2. If you have any questions, please bring them to class. Thank you.